Okay, so I'm just gonna go through this again very briefly for the purpose of this recording, since the class audio did not work out. Yeah, so I will reinterpret this again for those who will be watching this later on. Yeah, so for the box plots, so this was what was done in exercise 1, right? Descriptive statistics. So for the box plots, you usually want to interpret three things, right? When you're interpreting this, and let's change to maybe red. Okay, you usually want to interpret the center, the spread, and the shape of the data, right? And when you're doing data analysis, this is the first thing you do your descriptive, and most common among the descriptive is box plots and scatter plots when you're working with continuous. Okay, so let's look at these two and try to give some interpretation to these three things. For the center, you focus on the comparison of the median value, right? So we know that this point here is the median, this is the 50th percentile. Okay, so if we, and then this point here, okay, let's focus on that first and then we'll explain further. So the 50th percentile is the line in the middle of each box plot. Okay, so that could be the median, or you could look at it as the center of the data, because so for the center, we use mean, median, and mode, right, to capture the center of the data, these three items, okay? So if we have the median in the box plot as measure of center, then we can compare them, and we see here they are more or less the same, right? So an interpretation here could be that the median, in other words, the center of the data, or you could say distribution, for the BMI for both male and female are about the same. Right? And you know, in graphical interpretation, people, is subjective, right? Some people could say, hey, if you look at this, the female is slightly really bigger than the males, right? Just slightly, you know, but you could, of course, say they are the same, or just very slightly, females are bigger. It's quite subjective, okay? So we go to the second one, which is the spread. You know, as you noted in class, the spread for the female is obviously more or wider, right? And what do we use for the spread? For the spread, we normally focus on how scattered the data are. So if we look over here, we could use the outliers. If we're going to draw a histogram on top of this, it will look something like this. Right? If we do a histogram on top of this one, it will look something like this. Okay, so it's easy to even tell from these diagrams that the spread for females is wider, right? And of course, you see the outliers. Another way to think about the spread is the gap between the minimum and the maximum. Okay. You can also think about, yeah, essentially, if there are outliers or the minimum and the maximum could give you idea of the spread. So looking at this, it's obvious that the female BMI is more spread out than the male BMI, right? So we could say the female BMI is more spread out than the male BMI. Okay. And in terms of spread, we are talking about variance and standard deviation when you talk about spread. Right? So another way of stating this is to say that the variance for females is bigger than the variance of the BMI for male. Okay. And then a third interpretation, of course, will be on the shape. So again, if we look at this, looking at the histogram we've done, you see that this one is stretched out, right, on the right-hand side. So interpreting the shape, we usually use skewness. Okay, so we could tell that female BMI is right skewed. Is right skewed. Okay. And just a quick refresher, if you do this during the first week of class, you remember that this will be representing right skew, right? It could also be termed as positive skew. Positively skewed. Okay, why this is representing a negative skew or left skew. Could also be termed as negatively skewed. Okay, let's try that better. Okay, so but we see in the data that what we have is a right skew, right? The skew is on the right-hand side, which is a positive skew for female BMI. But for male BMI, it's more or less approximately normal. Okay, so that's the interpretation of this spread. Of the box plots. So you look at spread, you look at center, you look at shape. Okay, and you can put this in your own words in whichever way, but you're just describing what you're seeing. Okay. Any concern about this one? Is this clear enough? Okay, so let's go to the t-test, which is where you have a question. All right, so in the t-test, there are two things you interpret. I think I should minimize this a little bit so it will show clearly. You look at the group statistics, of course, but because you're conducting an independent t-test, this is actually your focus. This second table is your focus, okay? And so we said there are two things to look at here. And I'm going to enlarge this so that I could bring in the number, everything on one line. Some items will be cut off, but okay. I can actually move this one here and move this one here. Yeah, I think that works. Okay, this is better. Okay, so for the t-test, there are two sets of things to interpret here, right? The first set is over here. Let's draw that better. The first set is over here, right? And we could see the mark line here. This thick line is marking the gap between them. And then this second set is over here. Okay. So for the first set, I'm going to use different color to mark that. Let's use green. For this first set, or this first part of the result, you are trying to determine which of this line to interpret, whether to interpret the first line or interpret the second line, okay? And how do we know which one to interpret? We focus on the p-value here. So SPSS calls p-value SIG, significance level, or significant value. I mean, that doesn't rhyme with what we talk about in theory, but I don't know why it remains SIG here. Okay, so that is their design. So when significant value in SPSS output, SIG simply denotes the p-value. So essentially, this is the p-value for this test. And what is the test? The test is the test of equality of variance, right? It's testing whether the variances are equal. And you can see that on top of here. It's called Levene's test. So whenever you determine this test, that tells you which line of data to interpret. So the null hypothesis for Levene's test, as we stated earlier, let me use red for that. The null hypothesis for the Levene's test is that the variances are equal. Okay, if you want to write this in notation, then that will be written this way. Variance or population variance for group 1 is equal to population variance for group 2. Okay, that is the Levene's test, this section of the test. Okay, and then the alternative hypothesis is that the variances are not equal. Okay, so again, if you want to write that in notation, that will be something like this. That H1 is saying the variance of group 1 is not equal to the variance of group 2. Fine. Okay, so coming to your question, the p-value. How do we know when to reject and fail to reject? And I'm going to do that with, I think black will be better. So if the p-value of our test is less than alpha, we usually reject the null hypothesis. And this could serve as a review for quiz 2, actually, right? We reject the null hypothesis. Right? But if the p-value is greater than alpha, we fail to reject the null hypothesis. Okay. So just reading through this again, when you reject the null hypothesis, right, then you're saying whatever the null is saying is not correct or is not acceptable, right? So the null here is saying that the variances are equal for Levene's test. Levene's test for the null is the variances are equal. The Levene's alternative for the null, for a Levene test alternative, is that the variances are not equal. So when you reject the null hypothesis, it means you are saying the variances are not equal. And if that is the case, then you're going to interpret line 2 of this data in your output, right? If you reject the null hypothesis. But if you fail to reject the null hypothesis, then you are saying the null hypothesis is true, or you are willing to accept that. In fact, instead, we don't normally say the null is true. We say, that is what we're saying, we fail to reject. We cannot prove whether the null is false. Because we cannot prove it's false, we are willing to accept whatever it says. Okay, so the null hypothesis here is saying that the variances are equal. So if we fail to reject the null hypothesis, it means we are accepting that the variances are equal. So in that case, if you have equal variances is assumed, then you are interpreting the first line. Does that make sense? Yeah. Okay. So in this output, usually alpha is set at default of 0.05. So when it's not specifically given to you, you normally assume it to be given. Okay. So over here, if we go back to using red, we see that in this question, the p-value, which is equal to, for the Levene's test, right? So let me write that boldly here. We are right now working on the Levene's test. Okay. So we see that the p-value, which is equal to 0.929, is actually greater than alpha, which is by default 0.05, right? So if the p-value is bigger than alpha, then we are taking the second line. Because p-value is greater, we are failing to reject. So if we fail to reject, remember what we're failing to reject is the null hypothesis. So if we're failing to reject the null hypothesis, it means that we are actually saying that the variances are equal, or we are going to assume that the variances are equal, right? And so the interpretation we present is the one that is on the first row, right? Yeah. Do you have a question about that? Okay, so far it's clear, right? So pay attention that this is two tables, right? You have the Levene's test on the left, which will tell you which row to interpret. And once you've made that decision, then you move over to the right, here on red, to interpret the actual result for the independent t-test, okay? And so what are the interpretation here? Again, significance is the word SPSS used to present your p-value, okay? So this is talking about the p-value. So it's giving us the two. It's giving us the one-sided tail p-value. It's giving us the two-sided tail p-value. So we just interpret the one that is aligned with our interest. So let's assume we are doing two-sided tail test this time. So we're going to look at interpreting this result here, okay? You see that the p-value is less than 0.05, okay? And because of that, you are rejecting the null hypothesis, right? As we said here, if the p-value is less than 0 alpha, which is 0.05, we reject the null hypothesis. So we are rejecting the null hypothesis. So if you reject the null hypothesis, you are essentially saying that the two samples are different, okay? So, but let's write that down in more detail. So over here now, using green again for the independent sample t-test. Now that we've determined that we're going to interpret the first row, right, we pay attention to this p-value. The p-value here is less than 0.01, right? So we'll go over here and say, since p-value, which is less than 0.01, right? I think that might be a little bit confusing. That would be double less than, but I think I will just write it that way still. Yeah. Since p-value, which is given here as less than 0.01, is actually less than alpha, which we know to be 0.05, we'll reject the null hypothesis. Right? We'll reject the null hypothesis because p-value is smaller than alpha, right? And then you state your conclusion. Your conclusion will have to be aligned with your hypothesis test. So here we were testing the height for male and female, right? Whether they were independent, we were testing the height. Let's move this backwards so you can see that clearly. We're testing the height for male and female, right? In our data, 0 represents female and 1 represents male. And if you did exercise 1 clearly, this would have been replaced by the word male and female, right? Okay, so we're testing whether those two are different from each other. And so here we ended up rejecting the null hypothesis, right? And for avoidance of that, let me write that down here also. So let's move this down a little bit. Let's select all of that. Okay, so for each of these tests, we stated the null hypothesis for the Levene's test above here, right, is comparing the variances. The right-hand side, the dependent t-test is comparing the heights, right? So we are testing whether H0 here is that the mean height of group of males, for example, is equal to the mean height for females. Okay, that is your null hypothesis. And the alternative, H1, is that the mean height for males is not equal to the mean height for females, right? So since our p-value is smaller than alpha, right? Normally this would be like an actual number, you know, so, but because it's so small, SPSS just says less than 0.01, right? So because our p-value is smaller than alpha, we will reject the null hypothesis. And what is your null hypothesis? Right? The null is that these two heights, the mean of the two heights are equal. So if you reject that, it means you are saying they are not equal, right? So our concluding statement will reflect that exactly. So let me turn back to green. We could say there is evidence to suggest that the mean height for males is different from the mean height for female, right? Okay, so this is what we did theoretically in class, but in addition, after stating this, you are supposed to provide the evidence in parentheses. So how do we write that? And that is where the remaining component of this table comes in. So you're going to capture the test statistics, okay, as part of your evidence. You're going to capture the degree of freedom. That will give the person reading your work idea of the sample size. And then you're going to capture the p-value. These three things. right? So we go over here and write in parentheses to support this statement in Word, you will write that T, which stands for your test statistics, in parentheses. So this is standard notation. When people read this, they know that you're doing a t-test and that the degree of freedom is 298, we give that person an idea of your sample size, right? Because we know degree of freedom is N1 plus N2 minus 2. So that tells us that this is the total sample size is 300, okay? Is equal to, then you write your test statistics. So here for us is negative 14.771. Okay. And then parentheses, you have your p-value written. It's less than 0.01. So 001 or 0? Oh, 001. Okay. I've been using the wrong thing before now. So this should be 001. It's less than 0.001. Sorry?
Very tiny.
Very tiny, right? So SPS is just saying less than 0.001 to reflect the fact that it's tiny. So this is how to state the conclusion. And you just read it off of this table, right? Okay, so we see that the results here are more or less the same on both rows, right? They are quite close. In fact, the only difference we could see apparently is the degree of freedom, right? For both row 1 and row 2, the degree of freedom seems to be the only different thing there. Okay, so but in some other instances, these two results, the test will be much more different from each other. Okay. So but we pay attention to determine which one to interpret. We pay attention to this first segment of the table, right? The first two columns tells you which one to interpret, and we just explain that. Okay. Question on this? Makes sense, right? Okay, so essentially this is something we've done in class using hand. Yeah, the only difference is that now you have a large set of data. And so if you're dealing with, thousands of data, you can't do those manual work we did, right? But the manual work was to show what was going on in beneath. Okay, so in addition, the only thing we added here is the interpretation, the actual evidence in numbers, right? In class, we just interpreted it orally without putting the number. Okay? So that is really that. And if we go back to the paired sample t-test output, we can see that here. So if you look at this, you find that they are more or less stating the same thing as we have in the independent sample. They are similar, but the paired sample t-test doesn't have the test of equality of variance, even though some people still want to assess that in some other way, but we don't really focus on that here, okay? Because if you have a paired sample, the chances are that your sample size will technically be the same because it's a pair, right? And once the sample size is the same, the differences in the variance doesn't really matter much, right? But for independent sample t-test, the sample size could be different. And so because the sample size could be different, then any change in the spread of the data can actually affect how two of them can be compared, right? You want to compare apple with apple, not apple with oranges, right? But in terms of pair, all the time you have apple with apple because it's a pair. It's coming from more or less the same person all the time, right? So that because of that, you don't have the Leve's test here. You just have the output that you have here on the right-hand side. This output on the right side. That's just what you have. Okay. So the interpretation, everything I've done is just the same thing. The same thing. Okay. So over here, we look at this. In this analysis, we're looking at the height for twin 1 and twin 2, and we are comparing whether their heights were different. Okay. And then this is the test result. So over here, you have the t statistics, you have the degree of freedom, and you have your p-values for one tail and for two tail. Okay. And this is confidence interval. In independent sample t-test, also here, but just on the right-hand side, on the right end, instead of the middle or beginning. Okay. So how do we interpret it? the same way that we just did above. So over here, we focus on the p-value. And what is the test here? The test here is saying, so this is dependent. Okay. The test here is simply saying, is the height for twin 1 and twin 2, are they different from each other? So we can write our null hypothesis in Word. The heights are the same, or the mean heights. Right? You can use the word equal. And then the alternative, of course, is that they differ. Okay, so if you look at the results, again, you focus on your p-value. One tail or two tail, whichever is the option you're testing. But normally we do one tail when you're doing paired sample, right? So one tail here is less than 0.01 as before. So for that reason, so we could say again, since the p-value is, so we can put in parentheses, which is less than 0.001, is less than alpha, which is 0.05. Just as before, do we reject or fail to reject? We reject. We reject the null hypothesis. And as before, and we conclude in support of the alternative. There is evidence to suggest that the mean height of the twins does not differ. Oh, sorry, the mean heights of the twins differs. Okay, and like before, you just state the evidence in parentheses. So our test statistics with degree of freedom in the middle, in parentheses, the degree of freedom here is 146, right? 146. That test statistics is equal to negative 3.367. And the p-value is equal to, is less than 0.001, right? So essentially the interpretation, the way you interpret the independent and the dependent are really the same, right? But the difference is that when you're picking up your value, you pay attention to which one to use. In the paired sample t-test or the matched pair or the dependent sample t-test, you just have just one output because they are paired. But in the independent sample, you pay attention to whether the variances are equal or not, okay? And you can see whether they are equal or not from looking at the box plot, right? But this is subjective. As we say, some people are going to say the mean height for the mean BMI for female is actually slightly bigger than male. Some people are going to talk like that. Some people say we will not see that as significant difference. So they will just say it's about the same, right? So because this is subjective, you have the Levene's test to tell you whether those two valencies are actually equal, right? So if the Levene's test is, if you fail to reject the Levene's test, right? So if the p-value is bigger, then it means you are saying they are equal, because the Levene's test null is saying they are equal. The alternative for Levene's test is that they are not equal. So if the p-value here is bigger, then you're failing to reject the Levene's test. And if you fail to reject, it means if you fail to reject the null, it means you are accepting that null. So we're accepting that they are equal. So it means we're going to interpret the first row. But if we actually reject the null, assuming this p-value is less than 0.05, then we're going to go ahead and interpret the second row. Okay. But the interpretation for the dependent test, independent test, and that of dependent test are just the same, other than the first. Okay. Any other question or concern about this? Yeah. Okay. So this exercise 2, exercise 1 and 2 is doing the basic things we do when we are conducting independent testing data. You are expected to do your descriptive statistics first, and then kind of describe how the data is looking. And then you conduct your test to not say, you know, in number and in factual term, whether they are the same or different. Okay. Yeah. All right, so I'm going to stop the recording now. Next